mass times 0.
And
Y sine theta equals mv squared over r.
all right, so we have these two equations, substitution. We have a formula for weight. What's the formula for weight?
mg.
So y sine theta is equal to mv squared over r. Y cosine theta is equal to mg. Divide. I mean, there's several ways of doing it, but the simplest is we divide the left-hand sides and the right-hand sides. The y's cancel out, and I'm left with tangent of theta. The masses cancel out, I'm left with v squared over gr. And so, I asked you to find the speed.
Yeah.
Square root of gr tan theta. And then, because I gave you theta, r, and you can figure out g because it was on Earth. I assume it was on Earth. All right, so part B, you throw friction into it, and it is trying to find the, well, basically, no, set up this equations of motion. If there's friction, and we're trying to find the maximum friction so it doesn't start skidding. So if we go just beyond the maximum speed, which way is it going to slide?
Up the ramp.
Yeah. So therefore, friction must be acting that way. Which means we break friction up into its components also. And so this would be the friction force times the cosine of theta, and this would be friction times the sine of theta. And that gets tacked on to these, so we now have an additional piece here, and for the other one, now to get it into, and then I gave you the list of what variables are allowed. I don't think friction was allowed, but we do have a formula for friction.
U times normal force.
Yeah, more specifically, use of S. So, y cosine theta minus mg minus us y sine theta 0, and then y sine theta plus us y cosine theta. And solving it, I would do something similar and get mg over to the other side, factor y out, divide. And so the normal force is gone from the equation once I do the division, and then solve for whatever. I guess v. But you didn't have to solve it.
When you divide the left side, wouldn't it equal tangent of theta minus mu tangent of theta?
No, that would have been really convenient. Just doing the shorthand notation of c is equal to the cosine of theta and s is equal to the sine of theta, just so I don't have to write them out. If I factor the y out, I have y c minus mu s is equal to mg, and y s plus mu c is equal to mv squared over r. When I divide, I'm dividing the cosine by this whole thing, and dividing the sine by this whole thing, so it does not break down nicely into just a tangent.
What if you don't factor y out? Well, never mind.
You have to get rid of y somehow.
So your process of dividing the two equations is to get rid of y?
Yeah.
So it doesn't matter which one is in the denominator or numerator?
No, it doesn't. The reason why I did it this way was because I got tangent theta. Less important here since I'm not gonna get some nice neat trig function.
How would it be mu, or cosine divided by mu, and then minus u divided by sine in the equation?
If I divided,
Yeah.
I have c minus us over s plus mu c is equal to gr over v squared.
I would just keep it like that.
Yeah, then I would cross multiply. I'd get the cosine terms together, the sine terms together. Then square both sides. Substitute either cosine squared is 1 plus sine squared, or, sorry, 1 minus sine squared, or sine squared is 1 minus cosine squared. So I get in terms of the single trig function, solve that way. Other questions?
I still don't understand number 8 on this fraction.
All right, so going back to master set. Work, assuming force is constant. Is the force, the dot product times the displacement. Dot product is multiplying parallel components. So if I had I hat dot I hat, what would that equal? I hat dot j hat.
Is it 0?
Yes. So in the case of the circular orbit, pretend that's a circle. That would be the direction of my displacement, the instantaneous displacement at that moment, and the force is this way. No matter where I am, that's perpendicular to each other. So what is the work done for something in circular orbit?
The force of gravity times the displacement at that moment.
Okay, and which would equal?
Oh, 0.
Yeah. Yep, that's part A. And then part B, well, that's,
Some of it isn't parallel, right? Or perpendicular.
if something's not.
Wait.
Was that weight or right?
Oh, wow, I'm kind of confused on your response. I said, so when it becomes like an ellipse instead of a circle, that means part of the displacement isn't parallel to the force, right?
It's part is and part is not.
Yeah, so work isn't 0 anymore.
Correct.
Okay.
Ultimately, if you look at the total work, and this also goes to address problem number 5 there, I know that the total work is equal to the change in kinetic energy. Well, in this case right here, we have only one force, so the total work is the same as the conservative work. But if the total work is positive, then my change in kinetic energy is positive. In other words, the object speeds up. If the total work is negative, it slows down. If the total work is 0, no change in kinetic energy, stays the same speed. So when I'm grading number 5 under the total work greater than 0 equal to 0 less than 0, when you write it out, I'm picturing, all right, speeding up, slowing down, or staying the same speed. You feel more comfortable comfortable with number 8 now?
Yeah, I got that.
Okay.
I just didn't get the first explanation.
Other questions? I didn't ask any black hole questions on this, did I? No. I should add that.
No.
Not for this group, issue for the next group. But I would make sure you got credit. I just want to go through, I know there's a video on this, I just want to go through and I'm deriving the Schwarzschild radius for using classical physics. Planet X, I shoot some object out. Once it's launched, so we're talking about after it has been launched, what are the, tell me all the forces acting on the object?
Gravity from the planet. Force of gravity from the planet.
All right. Anything else? All right. So this thing is being shot out. The only force acting on it is conservative force. Energy is conserved. So my kinetic plus potential at this point, kinetic initial, U initial, is going to be equal to the same out here. And I put the little subscript G there because the potential energy we care about is the one associated with this gravitational force. I denied you last time, but I won't deny you this time. What's the formula for kinetic energy?
1/2 mv squared.
Much nicer. And so this is the mass of the object. Formula for this potential energy, the one associated with that force?
NV, no. Negative G, mass 1, mass 2, or mass of X, mass object, yeah. Divided by R.
Then that's got to be the same for the final. This object. Now we have the mass of the object is the same. We have that factor in every term, so it can go away. And now it's just a matter of figuring stuff out here. So what it is, and hopefully you can recognize that it's slowing down. And so what we're looking for here is the escape speed. How fast ultimately how fast does it initially need to be going so that it never returns? Well, but it's going to be slowing down the entire time. Well, what's the slowest it can possibly go?
0.
Yeah. Now, it'll be just slightly above 0 because if it ever stops, it would actually then start coming back. But it is going to be close enough to 0. This V final is going to be approximately 0. And since it's never coming back, what is, that's R initial and R final. What's the final distance?
Infinity?
Yeah. So something divided by infinity.
0.
Close enough. Yep. And so we've reduced this down to 1/2 V initial squared is equal to, go ahead and add that to the other side, big G mx over R initial. Solving for Ri, because ultimately doing the Schwarzschild radius, we get 2G mx over Vi squared. Now, the only thing that we can't really pull from classical physics that we do have to pull from semi-classical physics is the fact that there is a maximum speed. We cannot get faster than the speed of light. Yeah, I think that came on in conversation in this class before. So if we just stuck in the speed of light for that speed, if that's the maximum speed, this would be the sort of the radius of, well, the distance from the center of this to where it is. This would be the Schwarzschild radius. And I believe I would have talked about it in the video, if not in class. Now, there's much fancier physics to go along with this, the theory of general relativity and the curvature of space and time, but it comes out to the same answer. So from this, you can figure out the Schwarzschild radius of the Earth, or the Sun, or whatever star or object you want. All right. Oh, what the heck, let's just go ahead and do it. So how big would the sun need to be in order to become a black hole? Or how small, depends on the way you want to look at it. It's plug and chug. The x there, m sub x, is just the mass of whatever's creating the black hole. So it'd be 2 times g, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, times the mass of the sun, 1.99 times 10 to the 31st kilograms. The textbook here. That'll eventually come up. We'll confirm that. Divided by the speed of light, 3 times 10 to the 8 meters per second. And what do you get? And again, if you don't have your calculator here, just please make sure you know how to do problems like this on your calculator.
Gotta use that fancy A button.
Okay, yep. Oh, 10 to the 30th, not 31st. That's a negative 11 here.
11? Is that wrong?
Something's wrong.
Oh, wait, that's.
It's not 10 to the
I
11.
thought that was a 5.
I got same thing.
You also got 10 to the 11?
Yeah, that's times 10 to the 30th, right?
Yes.
Yeah, I got the same thing. Like the exact.
I got that to the 12.
All right, so (11 and 16 is 27. Yeah. I mean, if you did 2 times 6.67, 1.99, and then 3 squared. So the negative 11, that's right.
Oh, I forgot the square.
To the 29,496.
Sorry?
I need to get times 10 to that.
Oh, you got 29,000.
496.
I think you're off by a factor of 10.
2,949.6.
that here. Units?
Meters?
Like you mean it.
Meters.
It is meters.
Meters.
So just shy of 3 kilometers. If the sun somehow kept all of its current mass and shrank down to just under 3 meters, 3 kilometers, it would be a black hole.
Is that times 30 or 31 up there?
That's 30.
Oh, okay, that's what
Okay. I originally wrote 31 and then corrected myself. The 8.85, I was thinking that was right, but that's if the Earth suddenly shrank down. I think that's 8.85 times 10 to the negative third of the Earth.
So that would have to be the radius of the sun.
Yeah, that would be the radius of the sun in order to make it a black hole.
And that's what the Schwarzschild radius is.
Yeah. So as long as the sun is less than that radius, then it's a black hole.
Does that work for any type of mass?
Yeah. So if the sun suddenly became a black hole, what would the Earth do?
Continue its orbit like normal.
Yes. Not that we would last too long.
We have a solid 8 minutes to,
Pardon?
we have a solid 8 minutes to figure something out.
Well, after 8 minutes, everything would go dark. But we wouldn't die immediately because the Earth generates its own heat, so yeah. Things would start getting colder.
You said if the sun becomes a black hole, we wouldn't die immediately?
No,
Be a slow, painful death. Good.
That's what I've always wanted.
A black hole? We talking about a hole that sucks everything in, right?
that's the misconception.
Oh,
It
so-
doesn't really, it's not like a drain.
Okay.
If anything came within, there's all sorts of things floating through space. If anything came within the Schwarzschild radius, it would get sucked in. But it's not like everything, it's not a drain.